Hello again, this is Space Nuts. See, I told you I'd be back. Andrew-dunkley here. Great to have your company. And this is a Q&A episode, and we will be doing some homework. We had a question last time from Jens about why Titan has an atmosphere like it does, and Fred's done his homework, so we'll tell you all about it, Jens. We're going to look at tidal lock, a new theory about Planet 9 coming from one of our audience members, and we're going to talk about something we've not talked about much, but it wrote to us and said, you don't talk about me, so we're going to look at Triton, which is the moon of Neptune, and the use of Doppler. We'll talk about all of that through questions on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And the man on this particular mission is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It's good to join you from a slightly different location from normal, but that's fine.
Yes. Let's get straight into it because there is a fair bit on the agenda. We're going to revisit a question from last week, which came from Sweden. Yeah. It was Jens who was asking about Titan's atmosphere. What we might do is just play Jens's question. It's hard to say. Jens's question again. And then we can fill in the blanks.
Hello, Space Nuts. This is Jens from the forests of Dalsland in Sweden. As we all know, Saturn's moon Titan is a very special place. So here is my question. How did Titan become so special? How did it accumulate its thick nitrogen atmosphere and all its methane and ethane? There are dozens of moons of the outer planets, but only Titan has an atmosphere. What is it about Titan that made it become different from all the other moons? And another related question. It is often said that Mars is too small to retain an atmosphere in the long term. But Titan is even smaller. How come Titan can retain an atmosphere when Mars cannot? Thanks for a great show.
Thanks, Jens. We did determine that Mars probably lost its atmosphere because of its proximity to the sun, and it was all blown off by the solar winds. But we didn't determine why Titan might have the unusual atmosphere that it has and how it manages to retain that. Well, it probably retains it because it's far enough from the sun not to be as significantly affected as Mars was. But how is it that it's got such a strange atmosphere? That's the piece of the puzzle we needed to do some homework on, Fred.
Yeah, that's right. And it's actually not that hard to find some interesting theories about why Titan has a thick atmosphere, and various pieces of work have been done on this. The one that I think really puts it most cogently is a paper that was actually published in January 2019, and that was written by a group of scientists led by Kelly Miller, who's at the Southwest Research Institute in Boulder, Colorado, one of the big centers for planetary studies in the USA. And Kelly says, and I'm quoting here, a lot of organic chemistry is no doubt happening on Titan. So it's an undeniable source of curiosity. Because Titan is the only moon in our solar system with a substantial atmosphere, scientists have wondered for a long time what its source was. The main theory has been that ammonia ice from comets was converted by impacts or photochemistry into nitrogen to form Titan's atmosphere. While that might still be an important process, it neglects the effects of what we now know is a very substantial portion of comets' complex organic material. So what Kelly is saying there is that, yes, comets are mostly made of ice, but there is a significant proportion of them that are the organic chemicals that we know form the building blocks of life here on Earth, the carbon-containing chemicals. And so the theory is that those complex molecules have basically landed from comets and interacted with the surface of Titan. So you've got the sort of, it's a nitrogen atmosphere on Titan, which also has methane, ethane in it as well. And so stuff that would land from comets, these complex carbon-containing molecules, basically would react with the stuff that's already there. And so another comment from Kelly Miller: comets and primitive bodies in the outer solar system are really interesting because they're thought to be leftover building blocks of the solar system. Those small bodies could be incorporated into larger bodies like Titan, and the dense, organic, rich, rocky material could be found in its core. And that, if you have these organic chemicals that have found their way into the core of Titan, that's the underlying rock that sits under the ocean, that sits under the ice, then you've got a possible source of the gases that we see in Titan's atmosphere now. So what we're talking about here is an atmosphere that's been replenished over time, which is essentially why you have a body that's got an atmosphere where you might not expect it to have. So when Jens thinks about this a bit more, maybe have a look at that work, Kelly Miller from Southwest Research Institute. There is actually a nice space.com article that reports it, dated from January 26, 2019. Saturn's biggest moon, Titan, may bake its own atmosphere.
So it's just like cooking a cake in the oven. Everything you cook creates a gas. Yeah.
I think that's the bottom line, Andrew. Yes.
Yeah, clever. All right. There you go, Jens. Have a look at that article from space.com if you want to read more about it. But that's basically the theory behind Titan's atmosphere. Now, moving on, we have got a question from Ken. Ken comes from Maroochydore in Queensland. We've got a few Queenslanders sent us in questions for this week. Hi, Fred and Andrew. Why is tidal locking a function of proximity of the bound objects? Plus, do man-made satellites that need to point antennas, etc., to Earth automatically tidally lock, or do they need initial and ongoing manipulation to do so? Thanks, Ken. So a double whammy. Why is tidal locking a function of proximity of bound objects?
So it is a gravitational phenomenon, but in order for it to work, you've got to have a reasonably sizable object. So the whole thing about tides, Andrew, is that they're caused by, or what you might call tidal disruption, things that are caused by a tidal effect. The tidal phenomenon relies on one side of an object feeling a different amount of gravity from the other side. And so, for example, in the case of the Earth, the far side of the Earth feels less gravity from the moon than the near side does. And so that raises the tides on the Earth. And that process essentially involves a braking phenomenon, because as the Earth's trying to rotate, it's got this tidal pull from the moon, and that's actually slowing down the Earth's rotation. Now, the converse has been true over billions of years, and in fact, probably not that many, in fact, more like millions of years. The moon felt the same thing. One side of it was feeling more of the pull from the Earth than the other side. And so the braking effect was felt, and the moon's rotation slowed down until it was actually locked to be always facing the same side to the Earth. Now, spacecraft are too small for that phenomenon to have.
I was going to say, I'll bet you that the problem is the size of an object would be a major factor.
So, Ken, the second part of Ken's question is correct. Do they need initial and ongoing manipulation to point antennas to the Earth? And the answer is yes. They are directed, using thrusters to point in the direction that they're meant to. It doesn't happen by tidal locking. It's a nice idea, but they're too small for the time.
It would certainly simplify things, wouldn't it? If that could happen.
It would make it easy. You just put it up there and it turns on its own to face the Earth, but that's not how it works.
And our moon is not the only thing in the solar system that's tidally locked, is it? There's other moons that are tidally locked to their respective planets, and I think is Mercury tidally locked to the Sun? Is that
it's resonant? It's not exactly locked, but it's a similar process, so it's resonant, as is Venus.
Okay, there you go. So yes, Ken, it's it's a function of size. Size matters apparently when it comes to tidal locking. Good to hear from you. Thanks for your question.
Okay, we checked all 4 systems and team with a go.
Space Nuts.
Our next question comes from another Queenslander. His name is Ash.
G'day, Space Nuts. Ash from Brisbane here. Got a bit of a what-if question for you to wrap your thinking here around. I propose that planet Norrin once did exist. Out there in the depths of the solar system on its highly elliptical orbit, it came in and crossed paths with the one and only Uranus, giving it a smack on the way past, tilting it over. In the process, it loses its outer shell, making it the size it is now, and it lost a lot of its own momentum, making it drop into the inner solar system. Then gets captured by the sun, and we now call it Planet Mercury. What do you think? Great show, guys. Step up, good work.
Thanks, Ash. I think there's a bit of science fiction in that one. Only because I suspect that we know there's something in the far reaches of the solar system that's still impacting on the objects out there, and we haven't yet discovered what it is. But the mathematics says there is something. Therefore, if it's a planet, it's not Mercury. Would that be a fair assessment?
I think you've answered it quite well, Andrew. Very nicely. And Geordie agrees with you. You might have heard him just...
Yes, he does, yes.
Yelling in agreement there. Yes, it's the fact that we've got this alignment of far distant asteroid, trans-Neptunian object orbits that makes people suspect that there is a planetary body in the depths of the solar system. I think if you, if the scenario, and it's a complex but nicely elaborated scenario from Ash in Brisbane, if that had happened, I think these orbits would have now regularized so that the phenomenon would have disappeared, if you take Planet 9 away. And I think there would be other disruption in the solar system. I do like the way, though, that Ash ties in this peculiar orientation of Uranus, which is on its side, with the planet Mercury, which is mysterious. We think Mercury was once a bigger object because it's got a metal core that is too big for it. So we do think there might have been an impact there as well. So very nice thinking. Let's wait to see whether it becomes mainstream thinking, but I suspect its chances are pretty small, and for the reasons that you elucidated.
We can have a bit of a smirk about it, but he's been very clever in putting a few things together that we know and coming up with a theory. And theory is where you start when you're trying to solve these astronomical puzzles. So, why not throw it out there? Someone might pick up on it and go, hang on a minute.
Yeah, what you've got to do, though, is you've absolutely got to do the mathematical rigor on it all and make sure that all the equations add up and that it ties together and it's physically possible. Yeah. And that's, that's where you need people with that sort of background, which I don't actually have. Not anymore.
Neither does Ash.
Well, you never know. Ash might be, he might be a closet planetary dynamicist that we don't know about. Who knows?
Yeah, maybe. And I think we're overdue for a new song, Ash. Come on. You're dropping the ball, mate. No, but good one. I like his thinking. Thanks, Ash. This is Space Nuts. Andrew-dunkley here with Professor Fred Watson.
3, 1.
Space nuts.
Now, our next question, Fred, comes from another Queenslander. This is Nigel.
Hi, Fred and Andrew. This is Nigel from Brisbane, Australia. I have a hypothetical question about Neptune's moon, Triton. I believe Triton is said to be captured by Neptune. I hope I got that right. But what if it wasn't captured and it was still orbiting the sun out on its own in the solar system? My question is, would it be big enough to be a minor planet? And how do you describe a minor planet? Love the show. Keep up the good work. Thank you. Bye.
Thanks, Nigel. I think you'd call it Planet 10. Maybe.
Yeah.
How big is Triton, Fred?
It's 2,710 kilometers across.
So too small to be officially designated a planet if it wasn't orbiting Neptune.
No, that wouldn't be what would stop it being a planet. It's bigger than Pluto, in fact, if I remember right. Pluto's a little bit smaller than that. I got the number somewhere in my head. 1,680 miles or 2,710 kilometers. So it would be, without doubt, a dwarf planet because it's spherical. It's big enough for its self-gravity to have made it spherical, and that's partly the definition of a planet. But then to become a planet, it's got to have cleared its area of the solar system, becoming a dominant object, which it hadn't done. But the thinking is right. It would definitely have been a dwarf planet, and Nigel's correct in saying that the thinking is that it has been captured, that it probably is a trans-Neptunian object, a dwarf planet that has been captured by Neptune itself. And the reason why we think that is that it orbits Neptune the wrong way around. It's in what's called a retrograde orbit, which means it's going around in the opposite direction to Neptune's rotation. And it's actually the only big moon in the solar system to do that. There are a few of the smaller moons of, I think, Jupiter and Saturn that have probably captured asteroids that do that. But this is the only big moon, and it is the seventh biggest moon in the solar system. So it's quite substantial in size. So it would have been a dwarf planet. Now, the term that Nigel uses, minor planets, that's really an old-fashioned word or an old-fashioned term for what we now call asteroids. Minor planets were the posh term for asteroids. Asteroid was always, and I'm going back 60 years now or so, asteroid was thought to be a rather, a rather commonplace term that wasn't proper. And so if you were a scientist and you were working on asteroids, you would have called them minor planets. And in fact, the title of my master's thesis is Practical Techniques for the Determination of Minor Planet Orbits, because we didn't call them asteroids. And that was a suite of software to using these newfangled things called computers to work out the orbits of asteroids. So minor planet is a term that we don't now use. I suspect what Nigel's thinking of is dwarf planets. So it definitely would have been categorized as a dwarf planet.
Aha. Okay. So, yes, that doesn't surprise me at all, really. It's not one we've talked about very often. What kind of moon is Triton? And it must keep quiet because it's really embarrassed that it was a dwarf planet, but now it's been demoted to moon. I mean, it can't get worse. It can't get much worse.
It's once again, it's an ice world, we think. A crust of ice atop a probable subsurface ocean, and then, a rocky core in the middle. It is geologically active. And the reason why that's thought to be the case is that its surface is pretty smooth, without much in the way of craters. The estimated average surface age is less than 100 million years, and that now that sounds like a long time. But, for example, our moon bears the scars of the late heavy bombardment 3.8 billion years ago. So that's an old surface. So Triton has a young surface. And there's probably evidence of, maybe some evidence of there being geysers, ice geysers of the kind that we see on Enceladus and Europa. So it is a very, very interesting world, especially being a possibly captured dwarf planet. So it may have been formed much further out in the solar system. It's there's a number of things about Triton that make it very interesting, including its orbit. It's a very, very circular orbit, and it's thought that might have happened over the millennia, and because of usually if you've got a circular orbit, there's not much of a squashing and squeezing effect like we see on Io, Jupiter's moon Io, which is in an orbit that carries it nearer and further from Jupiter. And that squashing and squeezing is what makes it very volcanically active. Triton's is circular, but there is thinking that it still might have a warm interior from tidal heating, that squashing and squeezing that happens at a much lower level.
I just thought while you were talking, it prompted a question in my brain about where the word asteroid came from, if they were previously known as minor planets. And it actually came from the fact that William Herschel saw them and couldn't understand them. He was completely baffled, according to this article I've read. So he turned to another fellow who happened to be a poet, to come up with a name for them. And I'll just quote this. So the Sunday before the Royal Society meeting, Herschel appealed to Charles Burney Sr., a poet with whom he was collaborating on an educational poem about the cosmos. Burney considered the question and that night by candlelight penned a letter to his son, Greek expert Charles Burney Jr. The elder Burney suggested the word asterikos or stellular to describe the new celestial objects, and they came up with the term asteroid as a consequence. It didn't take off until the 1850s. They didn't. Yeah, obviously the the people, the big names in astronomy at the time went, not using that, but eventually it caught on.
Well, they were still saying that when I was a young astronomer. Oh,
were they?
Asteroids? Yeah, absolutely. It's a minor planet. That was the proper term for it. Anything else was vaguely commonplace, not the thing that we talk about. But yes, I do remember reading that actually, and it could have had a very odd name. Asteroid's a lot nicer than some of the things that were being suggested.
Yeah. Well, what was the other one? Stellulus.
Stelluli. Yeah, stellulus.
Interesting. Thank you, Nigel. Good to have a chat about Triton. We haven't done that very much. I'm not sure we ever raised it before, to be honest. But it's out there. It's doing its thing. It's feeling fairly forlorn, being demoted from dwarf planet to moon. It got itself caught. That's why it happened. One more question before we wrap up. This is a bit of a long one that comes from Robert McCowan, whereabouts unknown. I said that because he didn't tell us where he's from, but that's okay. Thanks, Robert. When a radar station measures the motion of an airplane or weather, it uses Doppler radar to tell if the target is moving toward or away from the radar by frequency shift. In other words, it measures the frequency change of waves or photons of the emitted signal. When we measure the signals from cosmologically distant objects like quasars and galaxies, we observe that they receive them at relativistic velocities. In this context, how is the difference of the Doppler effect observed on Earth and in the local universe different from the loss of energy of photons from the distant universe due to the expansion of space-time based on dark energy expansion? Wow. Is this an example of the change in the symmetry of translation explained by Emma Noether? And that's come from Robert McCowan. Noether, I think that's right. Emmy Noether. Emmy Noether.
Yeah. Actually, I think so. Robert's kind of answered it himself, because
that's a different.
Yeah, we do differentiate between the Doppler effect caused by motion, relative motion, and the cosmological redshift caused by the expansion of the universe, exactly as he says. So they are different. They're different things. They're sort of, how can I put this? The physical way in which they manifest themselves is the same. It's a shift of the wavelength of light towards the red end of the spectrum. But one's caused by a relative motion between objects, and the other is caused simply by the stretching of light caused by the expansion of the universe. And in fact, we can sometimes work on these two things together. In fact, I've been involved with this because in the early 2000s, the UK Schmidt telescope did a survey of about 136,000 galaxies, where we were looking at their redshift. In other words, the shift towards the red of their light caused by the expansion of the universe, the fact that the light was being stretched. We could measure that, but also we could work out what are called their peculiar velocities. And that is the independent motion of a galaxy when it's superimposed, if I can put it this way, on what we call the Hubble flow. The Hubble flow is the motion of galaxies as they're carried along by the expansion of the universe. But they've sometimes got their own individual motions on top of that. The usual analog that we give is it's a bit like imagine somebody in a boat on a flowing river, and that flow of the river is what's carrying them along, but they can move the boat around within that flow, so they've got their own peculiar motion. We do the same with galaxies. And the way you do that is actually quite clever. You can measure properties of galaxies that give you basically an estimate of their intrinsic luminosity, how bright they are, and then you can use that as a distance measure and compare that with the measure you get from the Hubble flow, and if they're different, that's due to the peculiar motion of the galaxy. I've not explained that very well, but that's how it works. So yes, the answer to the question is basically yes, and thank you very much.
Okay. Right. Excellent. Well done, Robert. And thanks for sending in your question. And don't forget, if you have a question for us, you can do that or send it to us via our website, spacenutspodcast.com or spacenuts.io, and click on the AMA link at the top. Now, we did have a question from somebody asking if there would be a better way of labeling the AMA link. And yes, that's a good question. And I've referred that one to Hugh, who's looking into it. But yeah, it is a bit of an obscure target when it comes to finding a way of sending us questions, but we're getting plenty of them, so I think most people are aware of it. But yeah, if we can relabel it, we will. I'm not sure what the process entails, but yeah, it's a work in progress. Thanks, Robert. Thanks to everybody who sent in questions, and thanks to you, Fred, for answering them. We really appreciate it.
That's a pleasure. I always enjoy having my brain stretched by Space Nuts listener questions. It's good stuff.
Yes, which can be measured using the Doppler effect. Yes, indeed. Thanks, Fred. We'll see you soon. And thanks to Hugh in the studio, who we won't see soon, but he's out there somewhere. And from me, Andrew-dunkley, thanks for your company. Looking forward to joining you again soon. Might be on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.